Hello everyone. Okay, so we've derived the chain rule. We've also, before that, derived differentiation from first principles, so we may as well continue in this light and derive everything else, which is going to be the product rule and the quotient rule, which are really important because obviously lots of our work in C3 is going to be involving product rule and quotient rule, so it's nice to know where they come from. We already know, just like how the last video was structured, that if y is a function of u and a function of v, and they're functions of x, so we've got two functions u and v and they're both functions of x, we know that when we differentiate them, this will be v dash of x times u of x plus u dash of x times v of x, or if you really like to go for it, we have dv over dx u of x plus du function of x dx times v of x. Right, that is really awful, so just write that again. So du of x. Alright, so we're going to prove this one here then. We're going to make that look like that. We'll start off, just like last time with first principles, by saying let f of x be u of x, v of x. Not going well today. Okay, v of x. And just like before, building up our ingredients then, we're saying that if we introduce that small change delta x, we're going to get the same ripple effect here of v x plus delta x and u x plus delta x. So when we put this into our first principles formula, we're saying that f dash of x is the same as the limit as delta x tends to 0 of u x plus delta x v x plus delta x minus u of x v of x all over our delta x. Now at the moment this doesn't look very much like what we have here, but it's starting to. All we need to do is a little bit of this clever manipulation, which is pretty nice. So let's get going with that then. In maths, you'll find that if you want something, you can have it, but you can never have it for free, is kind of the idea. So what we're going to do is, I'm going to do a little trick here, and I'm going to add a u of x and v of x plus delta x in here, and then I'm going to take it away. So I can't have anything for free. I'm going to add this and then take it away, and then put my u of x, v of x back in there. So nothing's changed. I haven't changed my object, but I've just done a little bit of trickery. Why have I done that? Well, this means that I can start taking common factors out. So here I've got, for example, I'm going to have u of x from here. Here's u of x and here is u of x. So I'm going to take out v of x plus delta x, subtract v of x, and then I've got plus, and this time we're going to do the same, but with the v of x plus delta x. And take this one out, and this is coming from here. So let's just eliminate what we've got so far. So I've used this one, and I've used this one, and in here I've used this one, which I'm about to finish, so that's u of x plus delta x, and then I'm going to use this one as well, so minus u of x here, and this is all over delta x. And can you see, we have it. We've got our u of x here, limit as delta x tends to 0, and because u of x has nothing to do with delta x, this u of x here, I'm left with x plus delta x, subtract v of x, delta x, and likewise plus, but this time our v of x plus delta x does have something to do with delta x, so delta x tends to 0, v of x plus delta x, all times by u of x plus delta x minus u of x all over delta x. And I can put my limit, I'll just rub that one out there. It just helps if we put all the limits separate so we can see what's going on at all times. So here are u plus delta x minus u of x over delta x. So there we go. If we snap like we normally do, we're going to snap our delta x tending to 0. We're actually going to take that limit. You have defined v dash of x here, haven't you? This thing here is the differentiation from first principles of v. Likewise, this is the differential first principles of u here. So this thing will be plus u dash of x. And notice that if we snap delta x tends to 0 here, tends to 0, all we're left with is v of x. So there we go. We've now proved the product rule. Okay, now we've got the quotient rule. So we just derived the product one, we may as well finish with the quotient rule. Like before, let's start by defining our f of x as u of x over v of x, and as we know, what we will end up with is v prime of x is our v of x all squared, remember v squared v, and then v of x u prime of x subtract u of x v prime of x. So, what we're saying is, using our first principles again, f dash of x is the same as limit delta x tends to 0 of u of x plus delta x over v x plus delta x subtract u of x over v of x all over delta x. Now, this thing here is fractions within a numerator. We don't like it, so we're going to put them all together. And this is just like algebraic fractions. We're going to make the denominator the same. So in a sense, we're going to, even though I don't really like the phrase, we're going to cross multiply, i.e. make the denominators the same. Really shouldn't be using this cross multiply language, but you know. Anyway. So notice that we haven't forgotten this delta x. This delta x is still going to fall into the denominator here, basic fractions. Now, same trick as before. I need to, because it doesn't really look like what I need, except for, notice I have a v and a vx plus delta x here. So when delta x snaps to 0, we're going to end up with that lovely v squared, which is what we wanted. So, let's move on. If we remember what we did in the product rule proof, we added something and then we took it away again, so nothing comes for free. So what I'm going to do is add this u of x, v of x, and then take it away again. So I don't change what I started with, but it's a helpful little trick to make it look like what I want it to look like. And likewise, it means that I can start taking out common factors. So here we have a common factor v of x, so I'm going to take that out, so that's going to remove that and remove that. So I've got v of x, and then we've got u of x plus delta x subtract u of x all over delta x, and we've still got our, let's go for minus then. We know it's going to be, as in I want a minus, but we just need to be careful here because I'm going to take out a u of x factor this time, so from here and here, so that removes that one if I immediately put v of x plus delta x, and we've also got this one here. Notice this is a plus, so in here needs to be a minus, which is exactly what we want. And remember, this is all over delta x, v of x plus delta x. And now this is looking absolutely lovely. So we're going to split our limits up separately just to show you what's going on. So we have our v of x plus delta x here. Limit as delta x tends to 0 of, remember this is all times because I'm taking that factor out, that denominator out. This is all times v of x, but remember that v of x has nothing to do with delta x. So I'm going to put that in brackets and write v of x, and this is all in big brackets, so v of x limit as delta x tends to 0 of u of x plus delta x, subtract u of x over delta x, and then we've got our subtract u of x again, nothing to do with delta x, limit as delta x tends to 0 of v of x plus delta x minus v of x all over delta x. Apologies, the screen is quite small. So that means we can actually take the limit. So as delta x tends to 0 here, you can see this delta x disappears and we end up with our 1 over vx all squared. At the same time, remember we have to take the limit simultaneously. This v of x has nothing changing, and this thing here is the very definition of the derivative of u. Here we've got our minus u of x, and again this is the very definition of the derivative of v. And what we end up with, as we wanted, remove that, we end up with our v of x, u prime of x, subtract u of x, v prime of x, over